Hello everyone. In today's lessons, we are going to solve two practice problems using TTT diagram, time temperature transformation diagrams to predict the final macrostructures and phase fractions for steel alloys, especially close to eutectoid region. I will show you step by step how to draw the full coding paths, identify all transformations, calculate weight percent using the lever rule that we talked about that in previous videos. If you have not watched them yet, please back and watch them first for knowing about the lever rule, eutectoid, hypo and hyper eutectoid, and finally TTT diagrams. Okay, so by using the level rule, we determine the type of perlite form, such as coarse perlite, medium, or fine. And by the end of this video, you will know exactly how to tackle similar problems in your practical engineering applications. Okay. Here we have a steel specimen containing 0.45 weight percent carbon. It's very important. Look at here. It is eutectoid. Okay? Means 0.76. When we are talking 0.45 means C naught is less than 0.76 and more than 0.022. So it is hypoeutectoid, if you remember. Okay. And for different carbon weight percent, we have different TTT. What's the meaning of that? Means exactly for 0.45, we can use this TTT. You cannot use TTT diagram for eutectoid, means C naught equals 0.76. So pay attention and use exactly the corresponding TTT diagram for a specific weight percent. Okay, it says that weight percent is 0.45%, austenized at 8.45. What's the meaning? That means above 8.45, uh, completely we have austenite and held long enough to form a complete uniform austenitic structures, means gamma or austenite. Using the isothermal transformation diagram or TTT diagram for a 0.45 weight percent carbon, iron carbon alloy, determine the final macrostructures produced by the following heat treatment. Identify the microconstituents presence and estimate their approximate percentage. First, the sample is rapidly cooled to 625 and held for 10 seconds, rapidly cooled again to 400, held for 5 seconds, and then quenched to the room temperature. Okay. Before I start, I want to talk about different regions that we have here. A means austenite, means here we have austenite, here we have austenite, up to here. So A is austenite. A plus F. If you remember, when we are hypoeutectoid, in hypoeutectoid, we have proeutectoid, ferrite, plus perlite. Perlite means the structures that we see exactly as 0.76. So here, this F here means proeutectoid alpha. You cannot write only ferrite because at perlite we have laminar layers of ferrite and cementite. So We are only talking about proeutectoid ferrite, means the needle shape um, that we have, that is for proeutectoid ferrite. So A plus F means austenite plus proeutectoid ferrite. It starts from this line. Yeah, okay. Means in this region, we have austenite plus proeutectoid ferrite. What's the meaning that? What's the meaning if we be here? We have. Why I explain you that we have proeutectoid ferrite means any temperatures above these temperatures, if we cool above, for example, if you consider it is 590, isothermos means keep that temperatures first, some proeutectoid ferrite we have. And after that, austenite, the residual austenite convert to another thing such as perlite, maybe medium, maybe fine, maybe coarse. It depends to the temperatures. So it is very important that if we cool any temperatures above 519, so if temperatures more than 590 for this weight person, definitely the final macrostructures contains proeutectoid ferrite. Don't forget that. Okay, what is the second zero line? The second zero line means 0% for converting to perlite. The blue line is 50%, and the green one is 100%. This dashed line is the border between perlite and bainite. Means in this region we have bainite. Above that we have perlite. But when we have medium, when we have coarse, when we have fine, you consider that here, for example, is fine. Here we have medium. And here up to another dash line, it is coarse perlite. So completely relate to the temperature. Okay. What about another I show by purple? Another dash line, this, this. It is for converting to martensite, means the top one for 0% convert to martensite, the second one 50%, and the last one 90% to martensite. Okay, so it tells that we rapidly cool to 625 when we are above 519. 625 is more than that. Definitely we have a proeutectoid ferrite, and it keep that. If quenching anything happens, it will not convert to anything. So why? Because only the residual austenite convert to some things. Okay. Here, at 1, we are here. From here, reach to this temperature. So at 1, we are 100% austenite. At 2 means keep that for 10 seconds. Look at here. The time here is 0.2 approximately. So plus 10 should be a little more than 10. I show 10, and you see that we are here. So at 2, because we are above this temperature, so we have proeutectoid alpha plus ferrite and perlite. Which perlite we have is important. You can consider it fine. Yeah, but the austenite converted to perlite fine means nothing. This 100%, some part convert that, and some part convert that. Then again cool to 400. Why you see this ramped and the ramped line. Why? Because we want to reset the time and we'll reach time zero and start again isothermal transformation or transition up to 3. If you remember from previous video, I told that only austenite convert to a bainite or martensite, remain austenite. Do you see any remain austenite? No, we have protectoid alpha or ferrite and perlite or fine perlite. So exactly same macrostructure, same as 2. Then quenching to up to room temperature, for example, 20 centigrade. Again, at uh, at 4, the macrostructures should be any remain at the 3. Austenite remain at 3, convert to martensite, but you look at 3, you don't see any austenite. It is protected ferrite and perlite or fine perlite. So the final macrostructures is protectoid alpha and perlite 100%. But finish, no, because the problem asks us identify or estimate their approximate percentage. Here you should use level rule. If you remember, and you can use the previous slide, is 0.76 here, and I show by another color, such as black. We are here, 0.45. Here is perlite. Here is ferrite. Which side far from ferrite? This minus this. So for ferrite, we can use that this for ferrite. Which side is far? 0.76 minus 0.45 per total 0.76 minus 0.022. What is 0.022? Maximum weight percent of the carbon in ferrite. That we say 0.74. What about W of perlite? W of perlite, exactly, we use the level rule, and it is a side that far from the perlite. It should be 0.45 minus 0.022 per total length. It is 0.76 minus 0.022. That for this problem is 58% perlite or fine perlite and 42% protectoid alpha or ferrite. Okay, next problem. Here we have samples of iron carbon alloy of eutectoid composition 0.76, means exactly we are talking about this carbon weight percent, exactly about 0.76. As I told you, for different carbon weight percent, we should use a specific TTT according to that weight percent. And here you see that isothermal transformation diagram for an iron carbon alloy of eutectoid composition. What is the eutectoid composition means? Means C naught is 0.76 weight percent. Okay. At is fully austenized at 760, producing a complete and homogeneous austenitic structure using the isothermal transformation diagram for eutectoid iron carbon alloy. Determine the final macrostructures that forms under the following conditions. Identify the macro constituents present and estimate their approximate percentage. Okay, it says that rapidly cool to 600. If I want to talk about that, it is not so complex as same as before. We have A is austenite here. We don't have any proeutectoid phase. What's the meaning of proeutectoid phase? If we are hypoeutectoid, proeutectoid phase should be proeutectoid ferrite. And if C not more than 0.76, we have proeutectoid cementite. So here we don't have any proeutectoid phase, only perlite and some phases that perlite convert that. In phase diagram only you see perlite, but here you see different things. You see the effect of time and temperatures on fine, coarse, medium perlite, bainite, or martensite. So A here is austenite. The red curve is 0% convert austenite to perlite or bainite because it's continuous C shape and it's cover perlite and bainite, both of them. The blue dash line is 50% and the green 100%. Yeah. So 600 hold for 4 seconds, then rapidly cool to 450 and held for 10 seconds, followed by the quench to the room temperature. Okay. At 1, we are 100% austenite. You see that we are in austenite region. We keep that or hold that for 4 seconds. At 4, we are at 2. You see completely aligned dash lines means 50% of austenite remain and 50% convert to perlite. Which perlite we can say that I think it is the border between perlite and bainite. I think 600 should be median. Then cool to 400. Again, you see that we back before 0%. Why? Because we want to reset the time and reset the process and see how convert that and keep that or hold that for 10 seconds. 10 seconds is here. So we have 50% austenite, 50% perlite. Only austenite has this potential to convert to other phases, not perlite, not bainite, nothing. So again, this dash line is 50%. So 50% of 50% or remain 50% austenite means 25% convert to bainite, 25% remain austenite, and 50% perlite. After that, quenching to the room temperatures, you see that we reach to 4. When we reach to the 4, only austenite has this potential to convert to other phases. So 100% of 25%. Why 100%? Because we below that M90% with 100% of austenite convert to martensite. Austenite at 3 was 25, 100% of 25 again is 25. Martensite 25 bainite and 50 perlite. What about the weight fractions? We calculate that exactly here. We don't use the lever rule. We use the lever rule for the hypoeutectoid or hypereutectoid. Okay. But if this problem asks you about the weight percent of ferrite or cementite, you can use the lever rule. Thank you so much. That is for today TTT practice problems. Remember, always show the full cooling rate and the time interval. It's very important and transformations and use the lever rule to calculate phase fractions. Be sure to specify the type of the perlite, not only mention perlite. Use the coarse, medium, or fine. And if you find this video was helpful for you, please like or comment and share, and don't forget to subscribe and turn on notifications so you will not miss future lessons on advanced material structures and mechanical properties. Thank you so much. Have a good one.